Supporting a non-uniform beam. A non-uniform beam L sub B equals 4.50 meters long and weighing W equals 1.40 kilonewtons makes an angle theta of 25 degrees below the horizontal. It is held in position by a frictionless pivot at its upper right end and by a cable LC equals 3 meters farther down the beam and perpendicular to it. So this is perpendicular to the beam. The center of gravity of the beam is delta LCG equals 2.00 meters down the beam from the pivot. So the center of gravity is here. Lighting equipment exerts a F equals 5.00 kilonewtons downward force on the lower left end of the beam. So there is a downward force here. Find the tension T in the cable and the horizontal and vertical components of the force exerted on the beam by the pivot. Start by sketching a free body diagram of the beam. So here is our beam. We have the center of gravity at 4/9 lb. So remember this was 4.5 nanometers. 4.5 divided by 9, 0.5 times 4, 2. So that's basically 2 meters down the beam from the pivot. So that's where we have it, the center of gravity. Now we have a cable attached to it at 6/9 lb. So that's basically 3 meters farther down the beam and perpendicular to it. So this is perpendicular to it. So if I draw a perpendicular here, this angle is theta, this is 90 minus theta, this is theta. Okay, and we have the weight of the beam here that is on the center of gravity. We have a downward force F, there's a tension, and then we have this pivot, so there will be additional forces on the pivot. So on the pivot, we have a vertical and horizontal component of the contact force. Here is the weight, and you can see that this is going to make an angle theta with the vertical as well. And then we have this downward force F, which makes an angle theta with the normal to the beam. So this is our free body diagram. It consists of the contact force on the pivot, vertical and horizontal components. We have the center of gravity delta LCG away from the pivot. We have the weight pointing down, the tension on the cable that's perpendicular to the beam. And then it is at a distance L sub C, which is 3 meters, 6/9 lb. And then we have this force, downward force F, that is at this lighting equipment on the lower left end of the beam. All right. So if I consider this coordinate system, X, Y, Z coordinate system, right-handed coordinate system, I can write the torque with respect to the pivot point in order to calculate the tension. Because if I write this torque equation, it's going to eliminate the vertical and horizontal forces, and I will be left with one unknown here, which is the tension. Okay, so let's start writing the torque. The net torque in the Z direction. Now we have the weight that has a component that is going to have a rotation effect. So if we take the component of the weight, W cosine theta, that's perpendicular to the beam. So this is going to have a torque R cross with F. So using the right hand, 4 fingers point from the pivot to the point of application of the force and curl them towards the perpendicular component of the weight. The thumb points up. So it's going to be in plus K hat direction. So we will have W cosine theta multiplied by delta LCG. That's the first one. Okay, so the weight W has a rotation effect. W cosine theta delta LCG is the torque. So remember, torque equals R cross F. Okay. Now I'm going to look at the torque effect of this force, downward force. So this is similar to the weight. I need to take its perpendicular component, f cosine theta, that's perpendicular to the beam. The distance here is the length of the beam LB, so it's going to have the same rotation effect. So this is going to be f cosine theta L sub b in k-hat direction. And now you can see that this has the same sense of rotation. It is trying to rotate it counterclockwise, right? This is also trying to rotate it counterclockwise. Now, if I look at the effect of tension, the tension is applied at a point LC from the pivot point, and it's already perpendicular to the beam. So if I look at R cross F for tension, you see this has a clockwise rotation effect. So it's going to be R cross F using the right hand from the pivot point to the point of application of the tension. Curl the fingers towards the cable, the thumb points into the board. So it's basically minus. So this is minus T L sub C. And since this is an equilibrium, the net torque should be 0 at equilibrium. All right. So with that, if I substitute for delta LCG 4 over 9 LB, and here I have f cosine theta LB minus tension LC is 6 over 9 LB. This must be equal to 0. So I see that the LBs will cancel, and I'm going to find the tension equals you can see that I can multiply this equation with 9, and you will see that this will become 4w cosine theta. This is 9f cosine theta, and this is minus 6t. So let's multiply this with 9. So I obtain 4w cosine theta plus 9f cosine theta divided by 6 for the tension, or I can write this in cosine theta parentheses. The tension equals, in cosine theta parentheses, I have 4 times the weight plus 9 times the force, 9f cosine theta divided by 6. So that's my symbolic answer to this question. Okay. Now we can plug in some numbers. W, the weight is equal to 1.40 kilonewtons. The force F is equal to 5.00 kilonewtons. Theta is equal to 25.0 degrees. So this gives us for tension 4W. So we will have 4 times 1,400 newtons plus 9F, 9 times 5,000, multiplied with cosine of 25 degrees divided by 6. So this will give us, for the tension, 7.64 kilonewtons. So that's our answer for tension. Now, how do I find these horizontal and vertical forces at the pivot point? So I can write the equilibrium condition on the x-axis. The net force on the x-axis should be equal to 0. Okay, so you can see that T well, let's say that this is this horizontal force is basically in the direction of the beam, and the vertical force is perpendicular to the beam. So let's check this carefully. horizontal and vertical components of the force exerted on the beam by the pivot. So horizontal force is along the direction of the beam and vertical is perpendicular to it. So the horizontal part will have basically so T sine theta will have this horizontal component. Okay, so that's not the right way to do it. So this is horizontal. This is vertical. Okay, so T sine theta will be the horizontal force acting on this because weight and force F are on the vertical axis. So if I write the net force on the x-axis, sum over the forces on the x-axis should be equal to 0. So the horizontal force, I have used this convention, it is pointing to the right in plus I hat direction. Horizontal force, then T sine theta is pointing in minus I hat direction, is equal to 0. So I find that the horizontal force is T sine theta. So that is basically, if I substitute what I have found for T, 4W plus 9F cosine theta sine theta divided by 6. So that's basically the horizontal force on the pivot. Now, if I substitute the numbers here, the horizontal force is equal to 4 times 1,400 plus 6 times 5,000 cosine 25 sine 25 divided by 6. This gives me a horizontal force of 3.23 kilonewtons. Okay. What is the net force on the y-axis? Now you can see the vertical force is being balanced by the weight, the force F, and the vertical component of the tension. So the first thing I did was consider the net force on the x-axis equals 0. Now I consider the net force on the y-axis equals to 0. There is this vertical force pointing up. There is T cosine theta pointing up. The weight and the force F are pointing down. So this is 0. So I have T cosine theta pointing up, WF pointing down, and the vertical force pointing up. So this gives me the vertical force should be equal to W plus F minus T cosine theta. So if I substitute for T what I have found, this is going to be let's see here. It's going to be 6W plus 6F minus 4W plus 9F cosine theta divided by 6. So that is the vertical force. And if I substitute the numbers, let's see if this is positive or negative. It's going to be 6 times 1,400 plus 6 times 5,000 minus 4 times 1,400 plus 9 times 5,000 cosine 25 degrees divided by 6. This gives me a vertical force of minus 0.53 kilonewtons. So I find that it is actually not pointing up, but it is pointing down. Okay, to summarize, we are looking at a non-uniform beam that is being supported by a cable. It is attached to a pivot point. It can rotate around this pivot point, and there is a downward force at the lower end of the beam. So drawing the free body diagram, I recognize all the forces, F pointing down at a distance length of the beam from the pivot point, the weight pointing down at a distance delta LCG 4/9 LB from the pivot point, the tension on the cable, because the cable is perpendicular to the beam, is basically in the normal direction, and if this angle with the horizontal is theta, this is 90 minus theta, then the angle the tension makes with the vertical is theta. And the tension is applied at a point 6/9 LB, which is 3 meters. The first thing I did was draw the free body diagram. So I recognized the force F, W, the contact force at the pivot point, vertical and horizontal components, and the tension as the forces. And here I also note the point of application of all the forces with respect to the pivot point. And first thing I did was write the torque equation with respect to the pivot point to eliminate the vertical and horizontal components from the equation. So the torque due to the weight and F are both in the counterclockwise direction. So using the right hand rule, I see that this gives me a plus k hat vector. 4 fingers point from the pivot point to the point of application of the force of the right hand. Curl the fingers towards the force, the thumb points out of the page. And for tension, it's reverse. It's going to be in the minus k hat direction. So looking at the perpendicular components, W cos theta, F cos theta, tension is already perpendicular to the beam. We have W cos theta delta LCG plus F cos theta LB minus T LC, because the tension is already perpendicular, is 0. I find the tension for W plus 9F cos theta over 6. Now we can substitute the numbers to get the numerical value. Then, to solve for the horizontal and vertical components of the force, I write the equilibrium condition on the x-axis. The horizontal force here is balanced by tension sine theta, the horizontal component of the tension, which gives me 4W plus 9F cos theta sine theta over 6 for the net force on the x-axis, giving me the horizontal component. All right, and the net force on the y-axis equals to 0, gives me this vertical force balanced by W and F and T cosine theta. So the V plus T cosine theta, they're both in j hat direction, and F and W are in minus j hat direction. So this gives me for the vertical force W plus F minus T cos theta. And when I substitute the numbers, I realize that V turns out to be negative. So it's actually pointing in the minus j hat direction.